Hello everyone. The title of this talk is New Extremal Bounds for Reachability and Strong Connectivity Preservers Under Failures. This is a joint work by Diptarka Chakraborty and myself, Keerti Choudhary. What are fault-tolerant preservers? A preserver is a sparse subgraph that maintains certain property, for example, connectivity, distances, etc., even after a bounded number of failures. Throughout this talk, we'll use K to denote the maximum number of failures. To understand this concept of preservers, let us consider the example of connectivity property. Under no failures for any graph G, a spanning tree with just n-1 edges is a sparse subgraph preserving the connectivity property. Now consider the case of k equals to 1 failure. If we delete an edge, say xy, then the surviving graph G minus xy is still connected. However, T minus xy is no longer connected. This shows that just this spanning tree isn't sufficient to preserve connectivity property of a graph, prone to even single failure. Now the big question is, can we make property preserving structures fault tolerant? In this talk, we focus upon sparsifying a graph to preserve strong connectivity and pairwise reachability property when the number of failures in the graph are bounded by k. The first problem we discuss is fault-tolerant strong connectivity preservers. As an input, we are given a directed graph and a parameter k. The goal is to sparsify G to compute a subgraph H, such that for any set f of k failures, the strongly connected components of G minus f are identical to the strongly connected components of H minus f. That is, for a pair of x vertices x and y, if there is a path between x and y in both directions in the graph G minus f, then there must also exist a path between x and y in both directions in the surviving graph H minus f. Now, what is known for this problem? For the closely related scenario of the undirected graph, it is known that if there are k failures, then to preserve the connectivity property, we can always have a subgraph which has kn edges, where k is the bound on the maximum number of failures. Now for strong connectivity property, the trivial bound we have is n square, which is the maximum number of edges in the graph. So the question we explore is whether for any k we can find a preserver whose size is truly subquadratic in nature. We positively answer this question and show that for strong connective preserver, we can always have a subgraph with order k times 2 to power k into n to power 2 minus 1 by k edges. Here, tilde hides the polylogarithmic term. For the special case of k equals to 1, we also show a construction that achieves a preserver with just linear number of edges. We'll now explain the techniques of our generic construction. Our analysis involves two separate scenarios depending upon whether an SCC is small or large in G minus F. The main idea for small SCCs is to use the color coding technique to separate a smaller SCC from the failing set. Such a technique was also used in the vertex fault tolerance spanner construction provided by Dynitz and Krautkammer. For handling the large SCCs, the main trick is to use random hitting sets of appropriate size. These, with high probability, will have a non-empty intersection with large SCCs. We now go into details of them. First is handling small SCCs. We sample a set J of size gamma 1, where gamma 1 is a parameter of our algorithm, and compute the SCCs of the remaining graph G minus J. The union of edges in SCC certificates in G minus J has order n edges, which are added to our subgraph H. In one such execution, with good enough probability, it can be ensured that for a small SCC C0 and a failing set F, we have that J does not intersect with any of the vertices in the SCC, so C0 lies in the graph G minus J, and the failing set is entirely contained in our sampled set J. Now, to boost the probability, we repeat this procedure multiple number of times and each time add the relevant edges to the subgraph H. Handling large SCCs. To tackle this, we make use of single source reachability preservers. For a source vertex R, a subgraph HR is said to be K fault tolerant out-reachability preserver if for any set F of K failures, the vertices reachable from R in G minus F are identical to the vertices reachable from R in HR minus F. Similarly, a K fault tolerant in-reachability preserver with respect to R can be defined. Here, it is ensured that the reachability is preserved for the vertices having a path into R. For both these questions, it is known that a preserver can be computed with order 2 to the power k into n edges. We'll now explain our algorithm. First step is to compute a uniformly random set R of gamma 2 vertices. Again, gamma 2 is a parameter of our algorithm. Next, we take the union of the K fault tolerant in and out reachability preserver of vertices lying in R. The corresponding edges are added to the subgraph H. We'll now show how it ensures that strongly connected components are preserved in our surviving graph. For a large SCC knot in G minus F, it can be ensured that C knot will contain at least one vertex of R with high probability. Let this vertex be smaller. As in and out reachability of R is preserved, by definition of strong connectivity, it follows that C naught will be preserved in the subgraph H minus F for any choice of K failures. Together, the techniques for handling small and large SCCs will provide us strong connectivity preserver of subquadratic size. Next, we come to the second question considered in our paper, which is fault-tolerant pairwise reachability preserver. Given a directed graph G with vertex set V and edge set E, a parameter K, which is bound on the maximum number of failures, and a pair set P, which is a set of vertex pair. The goal is to sparsify G to compute a subgraph H such that for any pair xy in P, if there is a path from x to y in G minus F, then there is also a path from x to y in H minus F. So H essentially preserves reachability for pairs lying in P. Now what is known? Under no failures, if we want to preserve reachability for a set P of size small p, then it is known that we can have a preserver with order n plus minimum of p root n and np to power 2 by 3 edges. This implies that if p is at most square root n, then due to the p root n bound, we can always have a preserver with just linear number of edges. For the special case of single source reachability, where the pairs are essentially S cross the whole vertex set of G, it is known that under K failures, we can compute a preserver with 2 to power Kn edges, and this bound is also optimal. However, for the general scenario of arbitrary pairs, currently nothing has been explored. So this is the focus of our paper. Note that for S cross V setting, the size of preserver simply increases by a factor of 2 on increasing the failure count by 1. A number of questions that we explore are: first, for single failure, up to how many pairs can we get an order n sized preserver? Under 0 failures, as I already told, the bound is at least square root n. So we ask whether the same holds for a single edge or vertex failure. Second question is, how does the size of preserver change when going from one failure to 2 failures? Recall, for the special case of S cross V setting, the answer is 2. That is, it grows by a multiplicative factor 2. We ask whether this is true for arbitrary pairs as well. Thirdly, can we always get a subquadratic size preserver when the number of pairs are subquadratic in count? Our results are as follows. For single failure, for pair set of size P, we show that we can compute a reachability preserver with order n plus minimum of p root n and n root p edges. Observe that this implies for up to root n number of pairs, a one fault tolerant pairwise reachability preserver also has linear number of edges. This bound is same as that of 0 fault tolerant setting. Also, it implies that for subquadratic number of pairs, the size of preserver is also subquadratic. On the lower bound side, we show that for n to power epsilon number of pairs, in dual failure case, at least n to power 1 plus epsilon by 8 edges are needed. This implies on increasing k by 1, there is a polynomial increase in the size of preserver. It also implies that for any arbitrary small number of pairs which are polynomial in count, the preserver size is superlinear. So we cannot expect an order n size preserver if the number of pairs are root n, which was true for 0 fault tolerant and 1 fault tolerant scenarios. In the remaining talk, we'll only discuss the p root n upper bound. Let us consider a vertex pair ST. A reachability preserver for ST under no failure is a simple directed path from S to T. Under single failure setting, a minimal ST preserver can be represented as union of two ST paths intersecting at only ST cut edges and cut vertices. As shown in the graph. The number of ST cut edges here differ for different choices of source destination pairs. In order to bound the size of preserver, we see how preserver for different choices of input source destination pair interacts. We now define the term H-opt. So recall that we stated for one fault tolerant SCC preserver, we can always have a subgraph with order n edges. This subgraph will be denoted by H of SCC. Now, define H-opt to be optimal subgraph such that H-opt plus HSCC is a pairwise reachability preserver for the set P. Consider a pair ST. Recall that preserver ST was union of two disjoint parts intersecting only at ST cut edges and cut vertices. Let the green path shown here be one of these two parts. Consider a vertex beyond this path and let H1, H2 be two edges incident to V lying outside the path. Suppose H1 is contained in preserver of a pair S1T1 and H2 is contained in preserver of pair S2T2. If both SITI paths before meeting V intersect at predecessors of V, then we show in our work that only one of the edges out of H1 or H2 is contained in the subgraph H-opt. Similarly, if both SITI paths before meeting at V intersect at a successors of V on the green path as shown here, then we prove that only one out of the two edges H1 or H2 lies in the subgraph H-opt. These two propositions together imply the following key property. Among all the SITI parts intersecting at V, at most two intersect the ST path more than once. So suppose these are all the paths which intersect and V, then except two paths, all will just meet this path once and then depart from it. And there will be two paths which will be intersecting the ST path more than once. Using this P property, we show that the size of H of is at most P square root n. And we already know that the size of HSCC is order n. This together implies the bound of n plus P root n edges. Now, an interesting question is, can we extend this idea to k larger than 1? The answer is no. This is because our starting point was that preserver ST under single failure can be expressed as union of two disjoint parts intersecting only at ST cut edges and cut vertices. However, for two or more failures, this property no longer holds. In fact, for more than one failure, preserver ST cannot be represented as union of small on number of ST parts. Due to this, we obtain in our lower bounds that the size of preserver is superlinear in n. Now coming to the future work, the first interesting question to explore is, can we obtain sparse fault tolerant pairwise reachability preservers for multiple failures? The second question is, for the single failure case, in our work, we obtain a bound of minimum of n root p and p root n. For the one failure, under zero failures, it is known that we can obtain a bound of p root n and np to power 2 by 3. So the question is, can we replace this np to power 2 by 3 bound by n root p? Thirdly, for the strong connectivity problem, for any constant number of failures, can we obtain a preserver with order n edges? The answer is true for single failure, and the problem remains open for k failures. That's all. Thank you very much